طيب، بسم الله الرحمن الرحيم. كنت اتكلمنا الليكتشر اللي فاتت عن اللينير ترانسفورميشن. خلينا نفتكر كده سريعا اللينير ترانسفورميشن between two vector spaces. بيبقى في عندي vector space V vector space W، يبقى في some transformation from this vector space to this vector space, and we call this transformation is linear if it satisfies these conditions. The first is transformation of the sum of two vectors u plus v equal the sum of the transformations, and the transformation of a scale multiple of the vector u equal to the scale multiple multiplied by the transformation of u. You look at this block diagram, it simply says that if you do the summation in the original vector space V and then the transformation to W equal to transform each vector and then sum the transformations. So here the summation is performed in the original vector space V. Here the summation is done in the W vector space. And the second condition, scaling here is done in V, however here scaling is done into the W vector space. So these are the main conditions for the linear transformation. Transformation of U plus V equal transformation U plus transformation V. Transformation of Cu equals C transformation of U. So for example, if you have transformation from P2, which is the vector space of polynomials of degree at most 2, which any polynomial in P2 can be written in this form: A0 plus A1t plus A2t squared. This is a polynomial in P2. So if you want to transform it to a vector space which is R3, so here we have some transformation to get a new vector in R3. And the vector is written according to some rule. The rule takes the coefficients and write it in a vector 4. So this is a vector in R3. So this is transformation from P2 to R3. So let's check the linearity of this transformation. Is this transformation linear, which means that it satisfies these conditions? For example, if I want to check the first condition, I'll take two vectors in the original space and then do the summation, then the transformation, and check if I transform each vector separately and then do the summation, I'll get the same value. So I'll take another polynomial in P2. Okay. So these are two vectors in P2, polynomials in P2, and then do the summation first. So add the corresponding coefficients to get U plus V. So U plus V would be A0 plus B0, then A1 plus B1t, A2 plus B2t squared. This is U plus V. And then do the transformation according to this rule. The rule is defined in the problem. Okay? So the rule here is to take just the coefficient and write it in a vector form. So this is my new vector belong to R3. And let's check if this is equivalent to transformation of U plus transformation of V. the transformation of U is simply A0, A1, A2, and transformation of V is B0, B1, B2. So actually, transformation of U plus V equal to transformation of U plus transformation of V. So this is the first condition for linear transformation. And similarly, you can check the second condition, and it is also satisfied. So the transformation here is a linear transformation. Okay. This is transformation of Cu, which is equivalent to C transformation of U. So actually what we did here is to map any polynomial in P2 into a vector in R3. If you look at the kernel and range for this transformation, we say which vectors here are mapped to the zero vector. This is called the kernel of the transformation. The vectors here that are mapped to the zero vector. So you simply put here 0 and see the original vector in P2. If you put 0 in R3, you will get that the polynomial would be the zero polynomial. So the kernel is the zero polynomial. And the range, you check all the vectors you get in the codomain. And simply, if you transform any polynomial in P2 with any A0, A1, A2, you will get all the vectors in R3, and hence the range would be the whole R3. Another type of transformation, you can think of the integral as a transformation. If you integrate, for example, a polynomial, definite integral from A to B, and let's check if this is a linear transformation. You simply check again the conditions for linearity. Here the transformation of any polynomial, you just integrate the polynomial. So if I want to transform the sum of two polynomials, it would be the integral of the sum, and from the properties of the definite integral, you can distribute the integral. So you get integral P plus integral Q, which is actually transformation of P plus transformation of Q. So actually this is the first condition for linearity. And similarly, you can check the scaling property. You will get again transformation of Cp equals C transformation of P. So the integral can be thought as a transformation from the polynomial space to the real line, and this transformation is linear transformation. So you can either do the summation, then the integral, or the integral for each one, then the summation. So if you take a specific example for this definite integral and take a polynomial in P2. So this integral actually maps the polynomial in P2 into the real line. So let's find the kernel and range for this transformation when P is a polynomial in P2. So I write any polynomial in P2 as a function in X. So it would be A0 plus A1x, A2x squared. This polynomial belongs to P2. And then integrate from 0 to 1. This is the transformation of the polynomial. So if you integrate this guy, you will get A0x, A1x squared over 2, A2x cubed over 3, and then substitute with your limits. you will get A naught plus A1 over 2 plus A2 over 3. This is the transformation of P, and this guy belongs to the real line. So we are transforming from P2 to the real line. Let's find the range, for example, for this transformation. The range would be subspace of your codomain, which is R. By inspection, can you get all the values that you get in R, which forms your range? For any A node, A1, A2, you'll get all the values in the real line, so we can simply say that the range would be R. So the range is the codomain, which is R. For the kernel, we said that we try to find the vectors that are mapped to 0. So the vectors that are mapped to 0, you put this guy equal to 0. A naught plus A1 over 2 plus A2 over 3 equal to 0. And I want to find what is the original polynomial that would be mapped to 0. So the polynomial actually is written in this form. So I can write this is the form of the polynomial which is in the kernel that satisfies this condition. So we can simply write that the kernel of T is, and then write the form of this polynomial with coefficients satisfy this equation. So you can simply read from here A naught equal to negative A1 over 2, negative A2 over 3. This would be A naught of the polynomial, and then you'll get A1x plus A2x squared. So any polynomial in this form would satisfy this equation and would be in the kernel of the transformation. Let's see some properties for the linear transformation. These are the main conditions. We will get some properties using these conditions. If you try to map the zero vector, when you have a linear transformation, you can think of the zero vector comes from putting here c equal to 0. So if you put here c equal to 0, you will get transformation of 0 equal c, which is 0, transformation of u, which is 0. So for linear transformation, it is always known that the 0 is one of the kernel of the transformation. You could have many vectors mapped to the 0 vector, but one of them must be the 0 vector. Okay? You can combine these two properties, this property for the summation and this one for the scaling. You can combine this into a general linear combination. If you want to transform linear combination, for example, of two vectors, transformation of C1 V1 plus C2 V2, for example, would be equal C1 transformation of V1 plus C2 transformation of V2, which is the combination of these two conditions. Okay. As we said, the kernel is defined to be all the vectors that are mapped to the 0 vector. And for the linear transformation, we know that the 0 vector belongs to the kernel. Actually, we can prove that the kernel is not just a subset from V, it is a subspace in V, which means that it satisfies the conditions for the subspace. If you remember the conditions of the subspace, if you take two vectors and sum, it would be in the set, and if you scale a vector, it would be in the set. So if you want to look quickly at the proof of this guy, assume that you have two vectors in the kernel, which means that transformation of both gives the zero vector, transformation of V1, transformation of V, and you want to prove that the transformation of their sum equal to zero also, which means that the sum belongs to the kernel. So by applying the property of the linear transformation, the first condition, so you'll get transformation of U plus V equal the sum of the transformations, and each one is zero, so you get the transformation of U plus V equals zero, which means that U plus V belong to the kernel. And similarly for the scalar multiplication, and these conditions guarantee that the kernel is a subspace. Similarly, you can prove that the range, which is a subset of the codomain, is also a subspace in the codomain. We know again that 0 belongs to the range, okay, because you have transformation of 0 equal to 0, so 0 is one of the vectors in the range. You can also prove the two conditions for the subspace. Let's have a look quickly at the first property. So if you have two vectors in the range, which means that W1 and W2 have pre-images in V. So W1 is transformation of a certain vector U, W2 is transformation of another vector. We want to prove that the sum, which is W1 plus W2, is an image of a certain vector. So again, using the property of the linear transformation, we have this property, and transformation of U equal W1, transformation of V equal W2. So we'll end up with W1 plus W2 is an image of this vector in V. So this guy belongs to the range. Okay. And similarly for the linear transformation. So this is the way we write the proofs for the range and kernel to be subspaces. The kernel is a subspace of V, and the range is a subspace of W. Okay. Let's have a look at this example. If you have transformation from R3 to R3, and you know the transformation is linear, and you know the transformation of the standard basis, which are E1, 2, 3, the columns of the identity matrix. So if you know the transformation of the standard basis in R3, we want to write the transformation matrix. As we said before, if you map from R3 to R3, so this is actually done by a matrix 3 by 3. You have a matrix here, 3 by 3, multiplied by a vector, 3 by 1, to give you a vector also 3 by 1. So this is a transformation from R3 to itself. So if you know the transformation of E1, E1 is 1, 0, 0. So if you know the transformation is 2, negative 1, 4. I want to write here the matrix that causes this transformation. So using the property of product, that is can be written as linear combination of the columns of the matrix using these as weights. So the first column must be this guy, which is 2, negative 1, 4. And similarly for E2, You want to multiply by E2, which is 0, 1, 0, to get the vector 1, 5, negative 2. So the second column must be 1, 5, negative 2. And similarly for the third one, 0, 3, 1. So actually the transformation matrix is formed from the transformation of the standard basis as columns. Okay. If you want to get the transformation of a certain vector, so you can get the transformation of any vector by multiplying by your transformation matrix, or you can get it using the property of the linear transformation by writing the vector x as linear combination of the standard basis. So actually x can be written as 2 by 1, 0, 0 plus 3 by 0, 1, 0 negative 2, 0, 0, 1. And then apply the transformation for both sides. So we'll get transformation of this guy equal transformation of the linear combination. And using the property of the linear combination, you can write 2 times transformation of this guy, 3 times transformation, and so on. And these transformations are actually the columns of the matrix A. Okay. If you know that this is the transformation of vector general x and y, find the transformation matrix from R2 to R2. So here the transformation matrix you have some matrix here multiplied by x and y, 2 by 2, such that you get the transformation x minus 2y to x plus y. So we write here actually these coefficients directly as we did before, 1 minus 2, 2, 1, to get this transformation. Okay. Let's now define the onto linear transformation and one-to-one linear transformation. We are going to use this in the next lecture to do what is called the isomorphism between two vector spaces. So instead of doing the linear checks, linear dependence, linear combination, and so on in the general vector space, I can map this to Rn and do reduction as we used to do. So let's first define the condition for this to be, for the transformation to be onto linear transformation and one-to-one linear transformation. So for onto linear transformation, it is defined this way. This is a formal definition. Linear transformation between V and W is called onto if every vector in W has at least one pre-image in V. So we have to guarantee that each vector in W has at least one pre-image in V. If you look at this mapping, we say that every vector in W has at least one, maybe two pre-image in V. However, for this example, this guy has no pre-image in V, so this is not onto. You can simply say that the transformation is onto if you find that your range equal to the whole codomain. So here the range would be W. Here the range is a subspace in W. So this is not onto, but this guy is onto. For one-to-one linear transformation, as you do for the one-to-one function, if I give you a value in W, I want to I want to have only one pre-image in V, not more than one. So this is the formal definition. A linear transformation is one-to-one if every vector in W has at most one pre-image in V. You look at this diagram. So here, if I give you this vector in W, we say that it comes from two pre-images, so this is not one-to-one. But here you have, for every one, you have at most one pre-image in V. You could have this vector which has not any pre-image in V, but still this is called one-to-one. Okay. Sometimes we use this definition for the one-to-one. If you have this vector in W, such that transformation of U equal transformation of V, this implies that U must be equal to V. We use this actually in some proofs for a one-to-one transformation. So let's check this for matrix transformation for some matrices and try to find conditions to know directly if this matrix transformation is one-to-one and onto. If you look at this matrix transformation, it maps actually vectors from R2 to R. So for example here, T of x equal AX, and A is 1, 2, X is general vector, x1, x2. So the output would be x1 plus 2x2. So if I want to check if this transformation is onto, the input here from R2 and the output here is a vector in the real line. So can you get the whole real line from this transformation? You can get for any x1 and x2. So the transformation here, you have the range equal to the codomain equal to R, so T is onto. To check if it is one-to-one, you can simply check if you put here any vector and try to find the pre-images. You can have one or more pre-images. If you have more than one, then it is not one-to-one. The simplest case to check the zero. If you put here this guy equal to 0, can you find the pre-image to be one vector or more than one vector? You can have many vectors, right? If this guy is 0, so you could have x1 equal negative 2x2 in general for several values for x1 and x2. So this transformation is not one-to-one. Okay. If I want to transform from R3 to R2, so the input would be a vector in R3, and the output would be linear combination of these columns using these weights. So we'll get x1, 1, 2, x2, 2, 4, x3, 4, 8. Again, I want to check if this is onto and one-to-one or not. Here you have a vector in R2, right? To be onto, you have to span the whole R2. But if you look at these vectors, actually these vectors are multiple from each other. So this is simply can be written as the span of any of them. So this would not be the whole R2. So the transformation here is not onto, okay? Because the range is not equal to the codomain. So t is not onto. Actually, how do you know this from a general matrix? You can know it from the reduction. If you do reduction and you find how many pivots, here you will get one pivot, right? Because these rows are dependent. But if you get two pivots, it means that you are going to span the whole R2, which means that the transformation would be on. So for a matrix 2 by 3, for the matrix to be onto, you have to get two pivots equal to the number of rows of the matrix. Then you will span your whole R2. What about one-to-one? For one-to-one, I want to check again if you have a 0, for example, vector. I want to check the pre-image of this 0. Or any vector, not necessarily the 0. If I ask you, for example, you have a vector 4 and 8. What is the pre-image of 4 and 8? You have, for example, x1 0, x2 0, x3 1. Or x1 equals 0, x2 equal 2, x3 equals 0. And so on. So you have many pre-images for the same vector. So this transformation is not one-to-one. T is not one-to-one. And similarly for the 0 vector, if I ask you how to get the 0 vector, you can get the 0 vector in different forms from different values for x1 and 2 and 3. So we can put, for example, this guy is -2, this guy is 1, and this guy is 0. So we'll get the 0 vector and many other vectors. So we'll have many pre-images for the 0 vector, so this is not one-to-one. So simply we have some theorems here to simplify the identification of the matrix transformation to be one-to-one and onto. For the onto, we simply, if it is m by n matrix, you find the rank of the matrix, and which is the number of pivots. And if the number of pivots, as you said, equal to the number of rows of the matrix, which is m, it means that the transformation is onto. And in this case, the column space will span the whole Rm that you are mapping to. For the one-to-one transformation, if you can find only a pre-image for the 0 vector to be the 0 vector, then the transformation would be one-to-one. Okay. So we can prove it. Actually, this theorem has two ways. That if the linear transformation is one-to-one, it means that the kernel is the 0 vector. And if the kernel is the 0 vector, then the linear transformation is one-to-one. And here are the proofs for these guys. If you look at the first one, if you say that T is linear transformation, of course, and if you know that transformation of 0 equals 0, this is a property of the linear transformation. And if it is one-to-one, it means that the 0 has only pre-image 0. Then the kernel of T would be only the 0 vector. So this is one way of the proofs. The other way, suppose that the kernel of the transformation is the 0 vector, and we want to prove that the transformation is one-to-one. We prove it through this property. If tu equal tv, I want to show that this must imply that u equal v. So from the property of the linear transformation, t of u minus v would be tu minus tv, but tu equal tv, which means that this guy is 0, and this guy is 0, means that transformation of u minus v is 0. But you say that the kernel is 0, so this guy must be 0, which implies that u must be equal to v. So this guy implied that u equal v, and this is the condition for the one-to-one transformation. So if I give you a matrix general 2 by 3, you can simply say that it is onto and one-to-one from these two theorems. First, if I want to check if it is onto, so I want to reduce it, and here it is actually in echelon form, and you have two pivots equal to the number of rows, then the transformation is directly onto transformation. Is it one-to-one? Check if it is one-to-one. We said that we have to check if the kernel is the 0 vector or not. What is the kernel of this transformation? The kernel is simply you are solving Ax equals 0, right? Which is the null space of the matrix. So we want to find what is x1, 2, 3 that causes this transformation to be 0. And we said that this is actually reduced, so you can see that you have infinite number of solutions because you have one free variable, x3, so the kernel is not the 0 vector. You will have many solutions, so the transformation is not one-to-one. If you look at this guy, the matrix here is 3 by 2, which maps vectors from R2 to R3. We want to check again if it is onto and one-to-one. For onto, I want to check the rank of the matrix. Actually, you need one step for the reduction to remove the third row. Okay, so we'll get two pivots not equal to the number of rows. So the transformation is not onto. And actually, if you do this transformation, 1, 0, 0, 0, 1, 1 multiplied by x1 and 2, you will get a vector x1, 1, 0, 0 plus x2, 0, 1, 1. This is a vector in R3. So it's clearly not the whole R3. It is a span of two linearly independent vectors, so it is a plane in R3. So this is why it is not onto. Is it one-to-one? Let's try to solve for the kernel or the null space of the matrix. Is the kernel equal to 0 vector? You will get x2 equals 0, x1 equals 0, so the kernel here is the 0 vector. Okay, so the transformation here is one-to-one. If you combine these two conditions, one-to-one and onto, we call that the transformation is isomorphism between the two vector spaces V and W. It's a Greek letter, actually comes from iso and morph. Iso means the same, and morph means structure, so they have the same structure, the two vector spaces. So we say that V and W are isomorphic to each other, or there is an isomorphism between V and W. And if you look at this diagram, let's check which one is isomorphism. If you look at the first one, you can say that the first one is a onto transformation. Okay, because the range equals the codomain, but it's not one-to-one. For the second, it's not onto, okay, and not one-to-one. For the third one, it is one-to-one, but not onto. For the last one, it is both one-to-one and onto, so it is an isomorphism between V and W. Next lecture, inshallah, we'll talk about using the isomorphism, as we said, to map any vector space to Rn and to check the linear independence and linear combination Rn instead of the other vector spaces. Any question? Shukran.